Good afternoon. My name is Charlie Yanechka, and today we're going to talk about how to obtain the best image on your Olympus video scope. We have a lot to cover today, so let me jump right in. I'm going to talk about the very basic process of how to generate an image, or rather how a digital image gets created, and it's going to be specific to video scopes. And then there are 4 steps in that image creation. And we'll go through each step, and the first 2 steps we will primarily look at very simple basic graphics to help understand these theoretical concepts on light reflection and lensing considerations. And then the last 2 sections will be relatively quick, where we will talk about and look at actual scopes, live image, and look at the differences and effects those settings have on your image. So the first process, or the first step in digital image creation process, is light. Of course, to have an image, you have to have light. An image is nothing more than a collection, an organized collection of light that is reflected off of what you are taking an image of. From here on out, I'm going to use the word targets, and what I mean by that is a specific area of interest in your image. In the video scope world, that typically can be something like a crack or a turbine blade or a little spot of corrosion. But more importantly, the target is the little specific part of your inspection that you really care about and need to take a picture of and maybe do a report or analysis on. So the first step, of course, is just quite simply light reflecting off of the target and then going toward the camera. The second step in the process is, of course, the light from that target collecting itself through the lensing, and then the lensing refocusing that light onto an image, projecting an image onto an electric imaging chip, which all, by the way, this lensing and the chip itself is all located in the distal end, the very small end of a video scope. The next step in this digital image process is the chip itself. The digital imaging chip generates an electric signal, which is then sent through the insertion tube and is collected by the image processor at the base unit. The fourth and final step is that video or image processor in the base unit of the video scope takes the electrical signal from the chip received through the insertion tube and generates a digital signal, effectively does some post-processing and turns it into a digital signal that can then be displayed on your screen, as shown here on this video scope. So this is a quick summary of the 4 different sections, the 4 different steps on a digital image creation. I have them arranged here with the word information and then processing of information in this arrow to illustrate the point that the image is originally effectively created, or rather the information for the image is created and collected in this first step. The reflection off of the target is where the image's information originally comes from. The lensing then uses that information to project the image onto the chip. The chip then uses the image information from the lensing to generate the signal. That signal is then used by the post-processor to generate the image on the screen. Now this is very important because when we go over all these 4 different topics, they're going to be arranged in a way that I'm going to spend more time on the first section because this is the best way to obtain the best picture. Spend more time and energy on controlling and understanding how your light exists and behaves in your environment, because this is where the information is created. Each subsequent step only has the information given to it from the previous step. So if you start with good information, you'll end up with good information. So the first step, light and reflective surfaces. We live in a world full of ambient light. As I'm sitting here in this room, if I were to take a picture of a family, that family would be amidst lighting inside the room or maybe outside underneath the sun, and the picture would be a fantastic image because of all of this abundance of ambient light. In the world of RVI inspections, video scope inspections, the environment is very dark. So the only light in that dark environment is coming from the video scope itself. there's almost never any ambient light in these environments, and that can become an issue when you consider things like hot spots. So you have effectively this camera generating all the light it uses in a very dark environment. And it's potentially an issue with regard to hot spots because all of the light for this internal inspection comes from this lensing down here on the bottom. This is a close-up view of a G-series direct tip adapter. The center here, of course, is the lensing, and then down here is what we call the light dispersion lens. All the light for your environment and for that picture comes through this small section. Now this looks relatively large on your screen here, but remember that this tip adapter is only 6 millimeters in diameter. So this light dispersion lens is actually very, very small and pumping a lot of light through it. So the intensity is extremely high. So things like hot spots are of a big concern because if you don't allow that light to disperse, then part of your image will be too bright and the rest of it will be too dark. So how do we manage hot spots and what do we do to mitigate their effect? So to make it simpler, again, as I mentioned, we're going to use and look at very simple graphics. The lensing will be represented by gray, the dispersion lens and the lighting itself will be yellow, and then blue is going to be the housing and the insertion tube, everything else. We'll rotate this direct view tip adapter and make it smaller and place it in the lower left hand of the screen. So here we have the end of our insertion tube dispersing all of this light into a dark area. By the way, the angle of this light here is typically larger on our Olympus video scopes, but I made it slightly smaller just to make it easier to illustrate the point that I'm trying to make here. So we are displaying all of this light into the environment. What will happen when we get high spots is that you end up taking a picture of something like a metal plate when it is too close to your tip adapter. So this represents a metal plate with a welding. So this bump right here is effectively some welds that you need to take a picture of. If the plate is too close to the tip adapter, you can see that almost all of the lighting from the tip adapter is still focused in the same amount of area as when it first came out of the tip adapter. It's too bright. Not only is it not covering the weld, but more importantly, this section of the plate is too bright, it is receiving too much light, and the rest of the plate is not receiving enough light at all. So the scope is going to have a hard time averaging out that image. You have a very hot, bright spot, and then the rest of the image is going to be too dark because this section is essentially eating up all the light generated from the tip adapter. So one way to mitigate that effect is quite simply move the tip adapter away from the plates or move the plate away from the tip adapter, whichever may be the situation. And what you do there is not only disperse the light and make sure it covers more area, but more importantly, you spread the light out so that you do not have one section of your image that is too bright relative to the rest of the image. So that's one quick, easy way to mitigate the effect of hot spots. It is a balancing act because you don't want to go too far away, because with video scopes and the lensing involved, there is a zoom, natural zoom effect as you get closer and then as you get farther away. So if you get too far, the target, the area of interest, is going to be too small. So it's a balancing act on making what you need to do an inspection on big enough while not getting too close to eliminates the chance of hot spots. Another way to mitigate hot spots is this plate right here, very naturally, is almost always going to be reflective. What you don't want to do is take a picture or even do an inspection where the tip adapter is perpendicular to the plate, as it is right here, because you'll effectively be taking a flash picture of yourself in a mirror, so to speak. So you're still going to have somewhat of a hot spot in this area that is directly across from the tip adapter. So one way to lower that chance of that sort of a hot spot happening is to angle the tip adapter relative to the environment. Now I have a live example that I'm going to show, but before I do that I want to show and describe what I mean when I discuss up and down on the actual image. So you'll see in a moment I have a live screen of a scope, and you'll see the up section of the screen. That is, the top of the screen represents up, and then the bottom of the screen represents down. On our G series tips and NX tips, direct view tip adapters, the down section on the screen, the bottom of the screen, represents the light that comes from below the tip adapter here and coming through or next to the light dispersion lens. And the top of the screen, that image, is the lighting that comes from above the tip adapter, or the lensing as it is positioned here. So what we'll do is, we'll talk about that in a moment, but before we get there, again, just to look at the graphics, to show you what I mean when I say up and down, if you angle the tip adapter so that your environment is closer to the bottom of the screen, you will have more of this hotspot effect. Whereas if you take this tip adapter and do nothing more than rotate it 180 degrees, you're allowing that light to disperse itself slightly more simply by rotating the tip adapter. You're still effectively the same distance from this welt, from the target of what you need to inspect. All you've done is rotate the tip adapter. And to illustrate my point a little more clearly, I have a live example of an actual video scope, which we'll go to here momentarily. So here on the top right of the image of your screen, you can see the actual live view of the scope. And I have my little box right here. I'm going to open it up so that you can see what we are looking at. We're effectively looking at a plate down here, and then the insertion tube is pointing directly at the plate. Now, this is a relatively extreme angle, an extreme example, but I'm doing it to make my point easier to understand. So I'll close this back up so that there is no ambient light affecting the welding. So what I want you to do is look at the end of this plate. Look at the end of the welding and the plate itself. This plate is full of corrosion. Right now you can't really see too much of the corrosion in the top portion of the image. And that is because your environment is closer to the bottom section of your screen. If I rotate this so that the environment is closer to the top section of my screen, you will be able to see the farther section of the plate more clearly. It may not show up very clearly through the webinar, but on the screen here, live, it is obvious. So let's pay attention to the bottom of the screen, or rather what will be the bottom of the screen, and see if we can see the corrosion a little bit more clearly. So again, I have not touched or changed any of the settings. All I've done is rotated the tip adapter 180 degrees. Again, it may not be showing up on the webinar, but on my scope here, it is brighter farther away. It's an extreme example. In your typical day-to-day case, this angle is not going to be as severe, but it is something to be aware of and just play around with and try to create a situation where your environment is closer to the top section of your image as opposed to the environment being too close to the bottom section of the image. Because when it is close to the bottom section of the image, there is too much of a hot spot, and the scope counteracts that by bringing the overall brightness of the overall image down slightly. So this is one of the main reasons why we want to mitigate the prevalence of actual hot spots showing up in our scope images. So now we will go back to the PowerPoint presentation, and we'll talk about tip adapters. So we just went through the first step on an image creation. That was quite simply the light and how the light interacts with the environment and gets projected onto the lensing. The next step is the lensing itself. Remember, the light gets collected by the lensing, and then the lensing projects an image onto the chip. This is a collection of all the 6mm G-series tip adapters. We have NX tip adapters, of course, and then a 4mm options. But for our purposes here, we're just going to discuss these. The first thing to consider is your field of view. 40-degree field of view and then the 80-degree fields of view are relatively specialized situation, especially the 40-degree one. That's typically used for large tank and vessel inspections when you need to see several feet away from the tip adapter. This tip has a very natural zoom effect and is a brighter tip because of that. The 80-degree is kind of middle of the road. If you need to see something that may be 1 or 2 feet away. A common example is if you're inspecting a gearbox inside or on top of a wind turbine, you may need to see a gear tooth 1 or 2 feet away inside the gearbox. An 80-degree is very effective in that sort of situation. 120-degree tip adapters are our most popular tip adapters, quite simply because of the wide range, wide angle of its field of view. And that allows you to simply see more of your environment when you're doing your inspection, which is what you need to do. Essentially, when you do an RVI, a video scope inspection, you're essentially searching. You're looking for something that you're not entirely sure even exists. You're essentially looking for a defect or a lack of a defect. So to see more of the environment is going to be helpful, which is why the 120-degree tips are more popular and common. So because of that, we're going to focus on them with regard to the differences between near and far focus tip adapters. So again, we're talking about lensing, and in video scopes that is specifically which tip adapter you have and which tip adapter you need to use. So with the 120-degree tip adapter for the direct view, this is the focal range of these two tips. And that simply means the distance that the target is from the tip adapter. This is the distance range that it can be and still be in focus. So it seems obvious. If I'm close, I'm going to use a near focus. If my target is slightly farther away, I'll use a far focus. That seems pretty obvious. But what is not obvious is in this overlap section. Let's say you are more than 19 millimeters away, which is about 3/4 of an inch, and less than 200 millimeters away. The question then is, which of these two tips can you choose? I've seen a lot of people who say, well, I can just keep my near focus on because it's still technically within the focal range. You always want to use the far focus tip if you have the option to. And the reason for that is quite simply it is going to be a much brighter tip adapter because of the way the lensing and the focal effect is done and created in the lensing. And the way that is done is essentially the near focus tip adapter has a much smaller aperture than does the far focus tip adapter. And an aperture is quite simply the hole inside of the lens system that the light is allowed to pass through. In order for this tip adapter to achieve such a tight 2 millimeter focal range, it has to have an incredibly small aperture. So it doesn't allow as much light as a far focus tip adapter allows through. So when you have a choice, always opt for the far focus because you will be surprised it is going to make for a much brighter and much better image starting at around 3/4 of an inch. So that effectively was the lensing system. That was the second step. The third and fourth steps, I'm going to go back to the actual live screen of the scope, and it's going to be relatively quick. I have the GX here, and we're looking at the same plates as we did before. And you'll see the brightness setting up here on the left of the image. I'm going to be moving the brightness up and down, and so you'll see this number move, and you'll see what effect it has on the actual image. So as I turn the brightness up, various things are happening. One of the first things is it's increasing the amount of light coming out of the insertion tube. It's also affecting things like exposure and gain settings. Now the exposure and gain settings are existing at the chip level. So again, this is the third step. It is the third thing to consider in your process of considering the best possible image. Now what I see more often is somebody turns the brightness up to about 6 or 7, and then they need a brighter image because the background of this image is a little bit too dark, so they turn the brightness up, forgetting that in the closer section of the image, it is starting to be washed out because the scope is still increasing the amount of light coming out of the tip adapter. And this happens, and they do this because you go into a large area that is where your target is far away, and then you leave the brightness at a high level and bring it here, and you'll see that the brightness naturally brings itself down because the scope automatically adjusts itself. But it adjusts itself within a range, and that range is relative to the brightness setting. So the brightness setting ranges for 11, the gain and exposure range is a lot higher than the gain and exposure range for, say, brightness level 3 or 4. So don't be afraid to consistently go back down. I generally like brightness settings around 3 or 4 to start with, because you'll see after about 4, you'll start to get some washout in the bottom section, the bright hot spot section of the image. So that is the first consideration when increasing or changing the brightness. Once you get to the point where you're starting to wash out, when the image becomes too bright in the area closer to the tip adapter, bring it back down and then press this gain button in the far right of the image over here. If I press this gain, you'll see this wider one show up on the bottom of the screen. Now what this is doing is, this is an advanced gain feature that only affects the dark areas of the image. Notice that when I pressed a wider one, this section of the image did not change its brightness at all. But the background really did change its brightness. That is, the background became brighter without having affected the brighter section. So if I press gain again, you'll see that this brighter section down here is not affected, but the darker area is. So again, the recommended path on generating a brighter image is bring the brightness up until the point where you start to get some washout, when it becomes too bright, there's too much light. And then if you still need some parts of your image to be brighter, you can use the gain feature, which will effectively change the wider settings. And so increasing it from wider 1 to wider 2 just simply adds more of that intelligent gain boost. So that was the third step. The last and final step, what I call the post-processing, which happens at the base itself of the video scope. After the image has been created on the chip, the signal has been sent through the insertion tube. It is now being processed into a digital image. When that occurs, there are some digital effects that it can do and alter to the image. And so what we'll do is go into image mode to illustrate a couple of these. Sharpness, all of these are very obvious, kind of a picture is worth 1,000 words. So sharpness is quite simply, if I press the far left one, paying attention to the welding on this image, you can very clearly see that as I jump all the way to the right, it is a much sharper image, and you can see the differences between the color and the edges. Things like cracks will show up a lot more clearly. 90% of the time, I see people use the sharpest section. The only time you don't want to use the sharpest section is if you have a video scope such as a 6mm GX or a 6mm NX with an incredibly high resolution. The NX at higher sharpness can actually pick up superficial scratches that aren't of any consequence, but do show up because of the high resolution, high sharpness. So bringing it back down to a slightly softer area makes those superficial surface defects less of a distraction. So that was sharpness. The next topic is saturation for post-processing. Quite simply, monotone is used maybe 5% of the time. Monotone does nothing more than gives you a black and white image. The big differences are natural and vivid. Vivid can look like a non-realistic image. Natural looks like the actual image itself, the actual color of the real world. People choose vivid sometimes to highlight things like corrosion or heat-affected zones. What vivid does is it makes things like, makes the color red pop and the color blue pop. So basically blues become more blue and reds become more red. So a good example here is this plate is full of corrosion. So you should be able to see that the plate is now more of a gray color under natural. And when I press vivid, it becomes more red. And the entire plate becomes more red because there's corrosion all over this plate. So that's saturation. Lastly is dynamic noise reduction. This quite simply is a reduction of the amount of noise shown in the live image, which we can see here in the background. Again, this may not be showing up in the webinar due to bandwidth issues, but in the background you do tend to get in the dark areas what we call noise in the image field, which is small little random bits of white pixels. So if that is a distraction or if it's too much, we can go to image mode, dynamic noise reduction, and turn it on. Honestly, this has become less of an issue currently because all of our current models have such an incredibly bright light source. This GX has an LED light source in the handle that is very, very bright. The NX has a laser diode in its base, so it's always bright enough. So the noise reduction is less of a feature that people use, but it's there if you need it. So next we'll basically close with a brief summary of the steps of digital image creation. So again, these are just simply the four main steps of generating a digital image. And they're arranged according to importance. So you start with light reflecting in your environment, control the light, and try to mitigate the occurrence of hot spots as much as you can, because that is where all the information comes from. The rest of these steps can only do what they can do is so much given the amount of information or the type quality of information you give it. And so then spend more time on the lensing, less time on the third step, and even less time on the fourth step. So spend most of your time on the first, then second, third, and fourth. So that's essentially it as far as my general presentation goes. Thank you all for your time and attention. Now is our Q&A session. I believe there's a section there to ask a question. So I think we may have some here that I can answer, and while I'm answering those, feel free to ask any more questions, and I'll be here as long as there are questions. So if you have questions about anything I discussed here, please put it in there and I'll answer as best I can. So the first question is there a difference between the brightness of a direct and side view tip? There is. It is not an easy, obvious difference to compare the two, because it's not always apples to apples, because you have a side view near focus and a direct view far focus. But in general, side view tips do tend to be less bright. Direct view tips tend to be brighter, simply because there's more lensing involved in a side view tip. You have a prism, which essentially bends the light at a 90-degree angle in order to achieve that side view function. And there's also more lensing in the light dispersion lens, so you have a smaller amount of light to start off with. And then the lensing essentially eats up some of that light, because the more glass involved in a process, the more of light that gets absorbed by that glass. The next question is there an issue with leaving wider on during your entire inspection? So if you remember, wider is the advanced kind of gain function where it just brings up the dark area of the image. It's a good question because in the past we used to say that it is a concern, something that you need to try to not use all the time, and the only reason for that is purposes of battery life. Wider uses a lot of processing power, which uses a lot of battery power. And so the lower the amount of battery power you have, the longer the battery, the lower the amount of battery demand you have, the longer the battery will last. And so not having wider on may help your battery, but not as much as it used to. So if it is a situation where you're trying to extend the battery life of your system, look at things like noise reduction, saturation, and wider, and basically lower the occurrence and use of those, and you'll help extend the life of that battery before you have to change it. So we'll see. I'll give it a few more seconds to see if anybody else has any more questions. I don't see any here at the moment. So while we're waiting, thank you all for joining. Again, I hope this was very helpful. We went over a lot of topics, and not all of these topics were something that you can use in your everyday inspection. But I think it's important to be aware of all of these steps and all of these processes that happen in generating an image, because if you understand how the scope generates an image, you have a better idea of how you can affect and change those variables to your benefit in creating a better image. We pride ourselves on doing a good job on generating a system that automatically creates a good image, but it is still not as intelligent of a machine as the inspector. So we do rely somewhat on some decision making with the side of the inspector. So having that information is helpful. So thanks again, thank you very much, and that is all for me today. Hopefully you will join our next RVI webinar series and all of our Olympus Inspection 360 series. Thank you and have a good day.